Hello everyone, I'm Dr. George Bartuska with the Florida Aviation Network. Welcome to Sky Insights. Today we'll be talking about ground and airborne weather radar for pilots. Normally a course like this or a presentation like this is a one-semester class. Sometimes we can do a review in an hour. I've got 30 minutes, here we go. We're going to talk about radar, how it works, some of the theory, and note, if you have or use an airborne weather radar system, the manufacturer of that system provides manuals and training for their system. This presentation is in no way is intended to counter or replace their system training manuals. For your information, most airborne weather radar system training videos are available free online. Now, America has the global $40 billion market. America has $15 billion of that market. There are major segments of radar. We're going to be talking about weather radar. Now, radar originally stood for radar detection and ranging, but it is now a word in itself. It's a system that uses radio waves to detect and track objects, measure their distance and velocity, and determine their direction from the antenna. Here's a simulation of a radar. A pulse goes out, it's reflected, it comes back, received by the antenna, and it shows up on a display. Simply stated, weather radar transmits a radio signal or pulse that reflects off an object, typically rain or hail, and creates an electronically displayed echo or blip. Note, weather radar detects only precipitation, not turbulence. Some radars have a turbulence mode. They can only detect turbulence if there's something in that turbulence to reflect the radar signal. We're going to talk about the four main types of radar that affect pilots. The NEXRAD WSR-88D, the terminal Doppler radar, the airport surveillance radar that for air traffic controllers. Right now we're at an ASR-11, and all the airborne radar units. The NEXRAD detects precipitation and severe weather, and there's about 160 of those around the United States. The terminal Doppler radar was designed specifically for wind shear and microbursts, and it will detect a gust front. The ASR-11, like I said, is for air traffic control, but also picks up weather. And the airborne units are for en route weather hazard avoidance and flight safety. This is an antenna of the ASR-9 previous to the ASR-11. The big antenna on the bottom is the actual primary radar. The antenna across the top is the secondary surveillance radar that interacts with the transponders on board the aircraft. Why are we here today? Well, weather radar has become the primary means of detecting, describing, tracking, and nowcasting or forecasting precipitation-laden and to a more limited extent, clear air weather over the contiguous United States. Okay, we're all familiar. In fact, we heard it earlier today about Captain Sully putting an Airbus A320 in the Hudson River when he had multiple bird strikes and lost all his engines. He landed the aircraft in the Hudson. Most people are not as familiar with the miracle on the Bengawan, the Solo River in Java in Indonesia, Boeing 737, and we're going to see that now. Okay, this was a case where the pilots unfortunately lacked training how to use their weather radar. They encountered both significant rain and hail. Unlike Captain Sully, where he lost both engines due to bird strikes, this airliner lost both engines due to incredible loads of hail and water. And it literally fell out of the sky. Luckily for the flight crew and everybody on board, once they came clear of the clouds, they were right over the Bengawan River, and he was able to put the aircraft down in the river with no loss of life. Now, let's look at what the National Transportation Safety Committee, it wasn't the NTSB because this was in Indonesia, let's look what they said about that accident. The aircraft had entered severe hail and rain during weather avoidance, which subsequently caused both engines to flame out. There was also a possibility that the weather radar showed attenuation or shadowing due to precipitation that was so thick, with the result that the reflection of the radar electromagnetic wave could not get through. Therefore, the weather radar display showed gaps, but after entering the precipitation, they became red. It is possible that the crew, based on their training and experience, could not identify such attenuation. Radar shadowing is and was a well-known phenomena, and the pilots actually might have been able to detect it if they had received better training on how to use their radar system. That's why we're here today. The system had a function which allowed the pilot to tilt the antenna of the radar up and down, scanning the clouds at different elevations to get better sense of the location of the heaviest precipitation. This could have shown that the gap was likely an illusion by revealing slightly lighter but still heavy precipitation either above or below. 3 other major aircraft accidents that did have loss of life due to what we're talking about today. One was Delta Airlines Flight 191 in Fort Worth, Texas, an L-1011. Another one was Pan Am Flight 597 in New Orleans International, a Boeing 727. And another was Southern Airlines Flight 242, a DC-9 in New Hope, Georgia. Now we always want to refer back to the FAR aim. Airborne weather avoidance radar is for avoiding severe weather, not penetrating it. No flight path through an area of strong or very strong radar echoes separated by 20 or 30 miles or less may be considered free of severe turbulence. And originally, our FAR aim said NEXRAD radar mosaic imagery shows where the weather was 15 or 20 minutes ago, not where the weather is now, because there was a delay in the scanning and the volumetric scanning and processing. However, an upgrade now shows where the weather is 1.5 to 2.5 minutes ago. That upgrade is called SAIL, Supplemental Adaptive Intra-Volume Low-Level Scan. What does that mean? That means it starts scanning at the lowest elevation of 0.5 degrees, goes up a couple scans, and then gives a readout. Then it goes back to where it left off and goes up again. Here we can see in this volumetric scan, the top picture is before we had SAILs, where you had to wait for it to scan all these scans from 0.5 to 19.5 degrees. Now with SAILs, it scans a little, gives you a readout. Comes back and scans a little more and gives you a readout. Now, what's the radio beam and radio detecting and ranging all about? Well, as on a typical oscilloscope, we have a sine wave. It's an oscillating wave of some type. And that wave has a wavelength. The wavelength is the distance between 2 peaks or 2 troughs or 2 nulls on the center line. The wavelength also has a frequency. In meteorology, we're concerned primarily with the wavelength because we know we're looking for raindrops and hail. Electric and magnetic fields. We have more familiarity with this subject than one might imagine. Our ability to see light emission and reflection. Believe it or not, light and radio waves are the same thing. Use of our cell phones, cooking in one's microwave oven, receiving an X-ray for medical diagnosis, and sunlight. These are all examples of electromagnetic energy, electric and magnetic fields oscillating in time and space. Here is what's in your microwave oven at home. It's a cavity magnetron. And it works just like a whistle, only instead of air going around the inside, it has electrons. So it puts out a certain frequency and a certain wavelength. But your microwave oven is putting out a continuous signal to cook something in the microwave. Radar is just the opposite, as you're going to see. It's microsecond pulses. Okay, so what is a spectrum? Well, here we're putting light through a prism to break out all the different colors or frequencies of the light. Here is the electromagnetic spectrum with radio waves on the left, through microwaves, through infrared, through that little bitty slit of visible light, then ultraviolet, X-rays, and gamma rays. With radar, we're concerned primarily with the microwave range. And as you can see on the bottom, we're using pulses. How can we get a handle on pulses? We're going to see that in a minute. The magnetic part of this is that when current flows through a wire, it creates a magnetic field around the outside of the wire. This is called the right-hand rule. You can see that the magnetic field is turning counterclockwise the same direction of the fingers of that hand. And if you take a compass and lay it over a wire and put a current through it, you'll see it make the compass move. Now, here's what that looks like in real time. One of these is the electric part, and one of them is the magnetic part. In meteorology, we're using the electric field to detect with. Now, we can also have dual polarization, where we use both a horizontal and a vertical, but today we're just talking about the basics. Now, most of us originally got exposed to this with AM radio, depending on your age, then FM radio, and today most cars have AM and FM radio. What does that mean? Well, AM stands for amplitude modulation. The fact that that wave is going up and down in height means we're manipulating the amplitude, the strength of the signal. The FM stands for frequency modulation. If you see the change in those wave patterns, that's how the signal is being impressed on there. Here again, we have AM in the middle, FM on the bottom. On the top, we have a Morse code signal from someone using Morse code. That is a continuous signal being broken up into pulses. Now, these pulses that we're going to talk about next are moving at the speed of light. Here's the most important slide in the whole presentation. 1 microsecond equals 1 millionth of a second. 1 millisecond equals 1,000th of a second. A 1 microsecond pulse, then 999 microseconds for receiving and listening time, leaves time for about 1,000 to 1,300 pulses per second. This is referred to as the pulse rep rate or the pulse rep frequency. Thus, about 6.18 microseconds to travel out 1 nautical mile from the radar antenna. Then you times that 2 for the return trip at 12.35 microseconds round trip. That's known as a radar mile. Thus, the radar receiver is in the listening mode 99.9% of the time. Let me say that again. The radar system is in the listening mode 99.9% of the time. There is potential danger here, and we're going to talk about it, but your microwave is transmitting 100% of the time. Radar is only transmitting 0.1% of the time. Now, what does this mean? How do we put a handle on this speed of light? The speed of light is 160,000 miles per second, or 300 million meters per second. At the speed of light, a radar beam could circle the Earth approximately 7.5 times in 1 second. It's really moving. So here again is that pulse width, rest time to listen. Pulse width, rest time to listen. Now, another problem we have, just as in the case of light with illumination, that when that beam goes out, it starts to spread out. And as the beam spreads out, we characterize that by what's called the inverse square law. The intensity of a radar wave decreases proportionally to the square of the distance from its source, meaning as you move farther away from the antenna, the wave's intensity drops off rapidly. Essentially, the energy of the radar beam spreads out over a larger area as it travels, causing the strength to diminish. Well, this happens both in the transmit form and in the receive. So as it transmits, it spreads out, and if it's reflected off a hailstone or a water drop, on the way back it's spreading out too. So we call that backscatter. So the detection system has to be really sensitive. And what are we really trying to see? Well, most of you are used to seeing a water drop drawn in the case of like something hanging down. Well, the real shape of a water drop, because of air friction, is a hamburger bun. That's the shape we're looking at in the case of water. Of course, a hailstone can be round or jagged. Back to the far aim. Personnel shall never stand nearby and in front of a radar antenna which is transmitting. When the antenna is not scanning, the danger increases. What they mean is if the radar antenna is stationary and it's on, it could hurt you, and we're going to see. Personnel should be advised to avoid the open end of a waveguide unless the radar is turned off. I'm going to show you some pictures of waveguides in a minute, but there's one picture there. A waveguide is a precisionally manufactured or machined rectangular tube to guide the wave. It works just like a stethoscope, only here we're not dealing with sound, we're dealing with radio waves. Personnel should be advised to avoid looking into a waveguide or into the open end of a coax connector to a radar transmitter because severe eye damage may result. Personnel should be advised that when high-power radar transmitters are operated out of their protective cases, X-rays may also be emitted. Stray X-rays can emanate from the glass envelope type pulsar, oscillator, clipper, or rectifier tubes, as well as magnetrons, like we talked about the cavity magnetron. Here's an illustration out of one of aircraft radar manuals. It's saying that boundary for possible injuries in this case is 6.7 feet from the antenna. Possible effects include the induction of eye cataracts and various physiological and thermoregulatory responses. Thermo, think a microwave oven, as body temperature increases. These effects are well established and form the scientific basis for restricting occupational and public exposure to RF signals. Here's another illustration from an aircraft weather radar. So in this case, the danger area is within a 5-foot radius. Here's the good news. After more than 60 years of research, there's no established evidence that RF radar exposure can cause cancer. Now let's take a look at these 4 radars again a little bit closer. The NEXRAD radar is S-band, we call it. It's at 10.5 centimeters, which is 3 gigahertz, but like I said, we're really interested in the wavelength. But notice the power, 750,000 kilowatts. The C-band radar, which is the terminal Doppler radar, is down at 5.3 centimeters, which gives it more sensitivity near the airport, and it's only 250,000 kilowatts. The ASR-11, the air traffic control radar, is again S-band, but it's 10 to 11 centimeters because it's constantly changing for security. It transmits at 25 kilowatts. And then all the airborne weather radars, they're usually transmitting at 3 centimeters, a lower wavelength to give better resolution, and they are 30 to 50 kilowatts. Now, here's that NEXRAD. By the way, well, I'll show that in a minute. Here's the inside of one of those radar antennas. That radar is 28 feet in diameter. And the reason it's so big is it gives us a narrow beam width. The narrower the beam width, the better sensitivity we have. These are some soldiers doing maintenance on an Air Force radar system. And people wonder, why do they put them inside that dome? Well, if you don't put a radar antenna inside a dome, when it's windy, the wind will grab the radar antenna for a while. Then when it comes around again, it'll be grabbed oppositely by the airflow, and that twisting back and forth ruins the gears and the gearbox in the unit that's turning it around. Once again, here's that WS-88D. You can see the beam width is less than 2 degrees, which is good because, remember, as it goes out, it's going to spread out. Here's a unit. If you look carefully, the waveguide is going straight down from the round ball and then to the left into the transmitter receiver building. Now, here's an example of what happens with the ground radar. We have a transmitted pulse in red. We have a target in blue, which we'll say is rain. The radar signal hits the rain. The pulses hit the rain. They're reflected, and we call that backscatter back to the antenna. Here we have the radar beam hitting an area of rain, but if that area is very intense, it will attenuate and absorb some of the radar energy, and we won't see a storm that's possibly behind it, which is what happened to those guys that put the 737 in the Bengala River. Here's a comparison of the WSR-88D ground radar and the aircraft radar. The aircraft radar, like I said, is a lower wavelength to give it more sensitivity, but it can't see the distance because the ground radar is 750,000 watts, whereas the aircraft radar is in the 30 to 50,000 watts. Now here we have a comparison of the ground radar. I'm going to skip here. We have the ground radar at the top. It has enough energy that no matter how many cells are in the thunderstorm, it'll be able to see them. But in the case of aircraft radar, when you're in the air, there will come a point where all of a sudden multiple cells in the storm will just look like one blob. Another thing that happens, even though the radar beam is traveling at the speed of light, the fact that the atmosphere has density changes, it causes the radar beam to bend. We call that refraction. There's different degrees of refraction. Some of them will bend it down, some of those will bend it up, and then we have ducting. You may be familiar with this if you know anything about acoustics and underwater acoustics and submarines in World War II. We have ducting just exactly like that, and if it ducks down too far, it'll pick up the ground and give you an erroneous reflection when it comes back. Now, because the Earth is curved, the radar beam gets higher farther away from the radar site. Here's a volumetric scan, as I talked about earlier. Notice the lower scan's at 0.5 degrees, the highest scan is at 19.5 degrees. You will see that you have a choice between base reflectivity and composite reflectivity. The base reflectivity is the reflectivity from the lowest elevation scan, 0.5 degrees. The composite reflectivity is produced at the end of the volume scanned after it's scanned all those things and then processes the data. Now, one of the limitations of ground-based radar is that directly above the radar we can't see anything. There is what we call the cone of silence. The way we deal with that is we overlap adjacent radars to fill in the blank space. This is a picture of the Florida Peninsula. We see Melbourne radar on the left and Tampa Bay radar on the left. They overlap each other. On the bottom we have Miami radar on the right and Key West radar on the left. They overlap each other to fill in that cone of silence. And like I said, near the radar, the beam is lower to the ground, but it starts to elevate because of the curvature of the Earth, and then we see the volumetric scanning at the bottom. So limitations of radar: refraction of the radar beam due to the atmospheric density and changes of density, the curvature of the Earth's surface, the cone of silence, and the beam spreading and storm location. Now let's look at aircraft radar in particular. This is a 737 with the radar dish on the front. Radars are also mounted on wing pods. You have to have the transmitter and the receiver today are the same unit, packaged in the same unit. And here's a look at those waveguides. They are high precision machined and or manufactured tubes that carry the radar beam to and from the transmitter and receiver. And like I said, they work just like a physician's stethoscope, only instead of carrying sound, they're carrying radio frequency energy. Airborne weather radar works much like ground radar. A radar signal is sent out through an antenna, which is located in the airplane's nose or pod on the wing. The radar processor determines how long it takes the signal to return and then calculates the elapsed time, how far away the target is. A typical radar system includes the things that I've talked about, and anything that gets in the way of the signal, such as rain, hail, or birds, or insects, will give a radar return. What's ultimately presented is a cross-section of the storm as a bird's eye view. Because airplanes fly at different altitudes and attitudes, the radar beam, where the radar beam must be able to change. The tilt is controlled by the pilot. Here we see a radar antenna on the left. We see a graphical representation of how much the antenna can tilt up and down. And here we see a control panel for a particular airborne radar vendor. And you can see the knob on the right is called tilt. Right now it's in the down position for 15 degrees down. What reflects best? Wet hail and rain are the best reflectors of RF energy. Then wet snow, then dry hail, maybe dry snow, and maybe drizzle. But there's got to be something there to reflect it back. Now, both the ground and airborne radars measure this in a system we call dBZs, decibels of Z, where Z represents the energy reflected back, the backscatter. And the color coding is very similar for both units. Here the magenta is extremely heavy precipitation, red is heavy, yellow is moderate, and green is light. And here on the airborne, it's basically the same thing. Magenta is extreme, red is strong, yellow is moderate, green is moderate or light. So we have to be scanning and we have to be looking. The weather is detected by using the radar and its control functions. That's the tilt and the gain. The radar display is analyzed to find the greatest area of convection within the thunderstorm cell. A red or magenta target is considered an area of highest risk. Once the image is analyzed, the process of danger avoidance begins. And remember what it says in the FAR aim. You are to avoid problems that you see on the radar, not try to skirt around them. The weather must, or not try to go through them. The weather must always be avoided laterally by at least 20 nautical miles from the area of greatest danger. There are specific shapes that indicate hail. A finger, a hook, a scallop edge, a U-shape. When you go through your radar training, it'll emphasize that. But here's something to remember, straight from the National Weather Service. There's no perfect ground or airborne method for detecting hazardous radar. Now I'm going to do a review in case you're going to watch this later and take the test. The reflected signal of radar waves is called backscatter. Radar waves travel in a straight line in a vacuum. However, in the atmosphere, they are curved because of air density changes with height. As the ground-based weather radar antenna rotates and transmits its pulse signal, the radar receiver listens about 99% of the time. Radar waves, as applied to weather, bounce back from echo or are reflected by precipitation. Radar does not heat the weather because radar waves are short-pulsed waves. Ground-based weather radar signals, waves, can be dangerous to humans near the antenna. However, airborne radars are considered safer because the pulse power is much lower. The radar's reflectivity or operational signal received signal is measured and displayed in dBZs, that's decibel Zs. Because a radar signal beam is transmitted by a focused antenna, the system relies on tilt for better coverage. The pilot or co-pilot, whoever is running the radar, needs to tilt that. Radar signals reflected from the ground are referred to as ground clutter. Although radar has become a word in its own right, radar originally stood for radio detecting and ranging. Radar uses electromagnetic waves just like light waves. Radar waves travel at the speed of light. Most airborne weather radar systems use a cavity magnetron to generate their signal. When a radar signal is attenuated, it is absorbed or scattered. Reflectivity is a measurement of the backscattered energy. As a reminder, if you have or use an airborne weather radar system, the manufacturer of that system provides manuals and training for their system. This presentation we've done today in no way is intended to counter or replace their system training manuals. And note that most airborne weather radar system training videos are available free online. So remember, it's better to be on the ground wishing you were in the air than in the air wishing you were on the ground. Thank you for joining us. This has been Dr. George Bartuska with the Florida Aviation Network. I'll see you next time with another weather topic. Now stand by for the number for your wings credit.